Today we're going to learn about statics, which is an application of several of the things that we've seen so far. It's going to involve both torque and net forces on objects. So let's get started on statics. Statics, this is a good example of a static situation. We have several objects interacting with each other, and I would say if this thing is at rest, so this here is not moving, it is at rest, and no acceleration, then it is in a static situation. All the forces and all the torques on it all add up to zero. And what we can do is we can use everything we know to learn something about how much tension is on that cable, how much torque is being exerted by the person on one end or the panda at the other end. And statics will let us solve all kinds of problems like this. Before we get to it, I want to do a brief review of torque and talk about different ways you can calculate torque. So for example, if I want to calculate the torque of an object at point A due to this force F, so I have an object here and there's a force F acting on it, and I want to find its torque around the origin. Well, I need the distance to the origin, the force, and the angle between the force and the position vector. And one way to calculate the torque we saw before is force times the distance times the sine of the angle between them. Another way to think about it is it's the force here, it's the position vector, or the length of this vector, times the perpendicular component of the force. Or you can think of it as the perpendicular component of the position vector times the force. So if we were to extend this force backwards here and find the component of the position vector that's perpendicular to it, then we get sort of another way to calculate the torque. So the torque is FD sine of the angle, or the perpendicular component of the force times the distance, or the perpendicular component of the distance times the force. As an example of this type of calculation, here is a bar on a hinge. Okay, so we have a hinge here, and this is a long bar, 5 meters long, and there is a force here, mg, on the bar right there. So let's do two ways of calculating the torque that this force is exerting around the pivot point represented by the star. So using this method here, okay, so we can say what is the force? Well, the force is mg. And let's give it a mass. Let's say the mass is 100 kilograms. And then there's the distance, which is, you see that it's halfway up here, so that the distance is L over 2, which is 2.5 centimeters, or 2.5 meters. And then there's the angle between them, right? And this is the angle here. And that angle is going to be, it looks like 90 plus 53.13 degrees, so it's going to be 143.13 degrees. So that's the angle that we're going to use. Actually, that would be phi, I guess. So we can calculate the torque this way. Fd times the sine of that angle. We're just interested in the magnitude for now. So when I calculate that, I plug in those three numbers, I get approximately 14,700 Newton meters. Okay, so another way to calculate this that maybe is a little bit easier is if we were to use the force and the perpendicular component of the displacement. So what we would do is we would extend this down here, and we would redraw mg here, and this here would be the perpendicular component of the distance, and that would just be 1.5 meters. So if I calculate the torque that way, then force times the perpendicular component of the force, I get the same answer. I get 14,700 Newton meters. And that's just sort of a nice shortcut to doing the calculation that comes in handy sometimes. So statics, well, basically it boils down to all the forces and all the torques on it all add up to zero, right? There's no angular acceleration, there's no linear acceleration. So when we solve problems using statics, we're basically solving these two equations, i.e. the net force on some object, all the forces add up to zero. And the net torques around some axis on the object add up to zero. This is the basis for all statics type problems. It's sort of a combination of linear and angular accelerations. And since we're going to be working in two dimensions, right? sum of the forces equals 0, that could be three equations, right? X equation, Y equation, and Z equation. We're mostly going to solve two-dimensional equations. So here I have a TV on a chair with a bottle and an ice cream cone for some reason. And if I was interested in solving this problem, we're just going to do it in two dimensions, right? We're going to have all the sum of the forces in the Y direction, all the sum of the forces in the X direction. And for the torques, we're only going to worry about torques around one axis for our problems for now, right? We're just going to pick an axis perpendicular to the page and calculate torques around that axis. So for example, here's the sum of all the possible forces acting on that television, right? There's mg acting on the television at the center of gravity. There's a normal force due to the ice cream cone, right? The ice cream cone has some force of gravity downwards and a normal force upwards from that TV. That normal force upwards from the TV is going to lead to an equal and opposite normal force downwards. Same with the bottle. Depending on the mass of the bottle, there'll be a normal force upwards on the bottle, which means the bottle will exert a force on the TV. And here's a normal force from the chair. So there's all these forces acting on this TV. So the sum of all those forces has to add up to 0. Sum of all the torques. We can calculate the torques of this thing around that little x in the middle. So we can say the torque of this thing plus the torque of this thing plus the torque of this thing. So those three torques. The torque due to mg at this case will be 0 because you'll notice the force mg is located at the pivot point. So there will be no torque. So sometimes you'll pick a pivot point at a certain location to eliminate that equation. So we're going to do some examples to see this. Let's do a couple simple ones here. Here I have a board, a 4-meter board with a weight of 1,000 newtons. Okay, so its weight is 1,000 newtons. And you notice that the total board has a length of 4 meters. So the length is 4 meters. And there's a little distance here, x, that each cone is from the edge, right? So we have a board sitting on 2 traffic cones, and we want to know what's the normal force that each traffic cone exerts on it. Well, you can probably guess what the normal force is. Let's draw, for this, we're going to draw an extended body diagram. Because we have to worry about torques and everything, we sort of draw, we don't use free body diagrams, we use an extended body diagram. So what are all the forces on this? Well, there's always going to be the weight, right, on the middle downwards, and that's 1,000 newtons. And there's going to be 2, so that's going to be right in the middle of the whole thing, right? So that's going to be 2 meters from one end and 2 meters from the other. And there's going to be 2 normal forces due to the cones, right? So there's going to be one normal force here and one normal force here due to the 2 cones. So we'll call that normal 1 and normal 2. Now the cones are equidistant on either side. So if the total weight downwards is 1,000, and this is nice and symmetric, it's not unreasonable to assume that the 2 normal forces will be the same and that they will add up to 1,000. So they'll each be, we can expect that our answer will be 500 newtons up for each of them, because 1,000 down, so there's got to be forces up that add up to 1,000. But let's do it the long way to make sure that it makes sense. And what we're going to do first is we're going to do the sum of the forces in the y direction equal to 0. What are the 2 forces upwards? Well, there's N1 and N2. And what's the force downwards? Oops. There's only one force downwards, that's the weight. Right? So we have 2 unknowns, N1 and N2, so we still need to do a little more work to get our total answer here. So what I'm going to do is I'm going to do a sum of the torques. Now what do I want to do a sum of torques around? Well, let's pick this location here. I'm going to do a sum of the torques around that little star spot. Let's say that adds up to 0. Now why do I pick that spot? Well, let's see what it means. So the torque means I'm going to do a torque due to normal force 1. Is that going to be positive or negative? If you look at normal force 1, it's going to try to rotate it clockwise, so that's going to be negative. What's the torque due to normal force 2 going to be? That's going to be counterclockwise, so that'll be positive, so that'll be the torque due to 2. And the torque due to the weight, well, that's actually going to be 0, right? Because the weight force, this force here is happening right at the pivot point, so that's not causing a torque. So that one is going to be 0. So now let's plug in for the 2 torques. So the torques, so torque 1 is going to be the normal force 1 times the distance. How far is it? What is this distance here? You see 2 meters minus 1.5 meters. So this distance here is 1.5 meters, just like this distance here is 1.5 meters. Right, so it's going to be minus n1 times d1 times the sine of 90 degrees, which is just going to be 1 because the distance and the normal force are perpendicular to each other in this case. And plus n2 d2 equals 0. And d2 and d1 are the same, so let's just call them both d. Makes it simpler, right? You notice the d's cancel out, and we get that n1 equals n2, which is, if you solve this, you see that n1 is equal to n2. Those two normal forces are the same in this case. So I'm going to plug that into here. And so n1 plus n2 is going to be equal to, let's say, 2n1. I'm just going to replace n2 with n1. Is minus the weight is equal to 0. So n1 is equal to the weight over 2. So n1 is equal to 1,000 divided by 2, which is 500 newtons, which means n2 is also 500 newtons. Right, so that's not too surprising. We have the weight pushing down and the two normal forces upwards. And everything worked out. We didn't even bother trying the sum of the forces in the x direction equals 0 because there's no forces in the x direction in this case, so that's not a very helpful equation. But we had two unknowns and we got two equations to solve them. So here's a similar problem. The difference is that the cone has now been moved over, right? So it's no longer equidistant on either side. So the cone is now sort of on the right side is slightly further in. So if I were to draw a an extended body diagram for this, I have the weight force here, downwards, 1,000 newtons, and there's going to be a normal force due to cone 2 here, and there's going to be another normal force due to cone 1 here. And we can expect that the normal force will not be the same in both cases again, not like last time. So let's do the same procedure that we did before. Let's do the sum of the forces in the y direction is equal to 0. And so what are the two forces upwards? Well, there's the normal force from 1 plus the normal force from 2, and then there's one force downwards is equal to 0. Right? So now we have a beginning to this. What do we need next? We need, let's say, the sum of the torques. Let's do the sum of the torques. And what I'm going to do here is I'm going to do the sum of the torques around, and for this spot I'm going to pick the pivot point to be right here where n1 is. And the reason I choose it there is because when I do the equation, now remember the torque on the pivot point, there is no torque. So n1 is not going to be in this equation, just n2 and the weight. That means we're going to get an equation for n2. So if in order to solve this, I need these two distances here, right? So this is the distance for the weight force, and that is from 0.5 to the middle, so that's, I believe, 1.5 meters. We also need the distance between n1 and n2, and that's the distance of 2 to the center, and it looks like it's 2 meters away. So now, the two torques. So there's going to be one torque counterclockwise, which is the n2 torque, and then there's going to be one torque clockwise, which is going to be the torque due to the weight. Remember, n1 is 0, so it's going to be, let's see, n2 times d2 minus weight times that distance due to the weight. So if we solve for n2, we get the weight times the distance to the weight divided by d2. So my weight is 1,000, dw is 1.5, d2 is 2, and I get 750 newtons. Let's plug that into here. Solve for the weight. No, I want to solve for n1, right? So n1 is going to be equal to the weight minus n2. So 1,000 minus 750. So I get 250 newtons. So we have the two normal forces, right? The normal force closer to the center of gravity, remember the center of gravity is like here, the normal force close to the center of gravity is going to be stronger. It's sort of bearing more of the load than the cone further out. In this example here, the cones are equidistant from the center again, but we now have here, Sir Oinkington is a little pig, and he has a mass of approximately, let's say he has a weight. The weight of Sir Oinkington is 300 newtons. Okay, and he's 1 meter in from the edge. So what we can do now is, well, you can guess here what's going to happen, right? Which normal force is going to be larger? The normal force on cone 2. But let's draw an extended body diagram and figure it all out again. So here's my extended body diagram. I have the weight, the regular, the weight that we had before. Now Sir Oinkington has a weight of 300 newtons. That means the board is exerting a force upwards of 300 newtons on it. That means Sir Oinkington is also exerting a force downwards on the board here, so the normal force is going to be equal to 300 newtons as well. And this one, just for fun, is 1,000 newtons, right? Let's see. There's going to be a normal force here due to cone 1, and there's going to be a normal force here due to cone 2. So all those forces should add up to 0. And just to get ahead of the game, let's calculate all these distances. I'm going to end up picking this as my pivot point. So let's see. This distance here is 0.5 meter, so we'll call that d. That's the distance of Sir Oinkington, so 0.500 meters. There's also the distance from the pivot point to the weight, right? And we'll call that the distance of the weight, and that's 1.50 meters. There's also the distance all the way out here, right? Distance 2, and that is 3.00 meters. So we have the distance of all those forces around our pivot point. So let's do it again. Sum of the forces in the y direction equals 0. So N1 is upwards, N2 is upwards, and there's 2 forces downwards, right? The one normal force due to Sir Oinkington, and then the work on the weight of the bench or the board. So there's 2 unknowns there, right? We're gonna do torque. What are we gonna do torque around? We're gonna do the sum of the torques around that star at the far end again, right? So we end up with minus the torque of Oinkington because he's pointing it clockwise, and then there's minus the torque due to the weight that's also clockwise, plus the torque due to 2 is equal to 0. So I plug in everything I know here, right? Minus the distance Sir Oinkington times that normal force minus the distance of the weight times the actual weight plus the distance to 2 times the normal force 2 equals 0. So I can solve that for N2, and that's dO NO plus dWW over d2. When I plug in everything, I get about 550 newtons. So I'm going to plug that into here to get N1, right? And when I solve this for N1, I get NO plus the weight minus N2. When I plug in everything, I get 750 newtons. So let's think, does this make sense? 750 plus 550, that's 1,300 newtons upwards. And if you look at the total, there should be 1,000, right? If you look at the total force downwards, it's 300 plus 1,000, so that's also 1,300 downwards. So this works out. So in this problem here, we have a sphere, radius 4.2 centimeters, and a mass of 1 kilogram attached to a wall by a rope, as shown. The center of the mass of the ball is 8 centimeters below the attachment point. So this just means that this here is 8 centimeters. And it has a radius of, so here's the radius r, right? And that r is 4.20 centimeters. So we can use that to calculate the angle theta, right? So let's calculate this angle theta right away. We're definitely going to need that. Tan theta is equal to opposite over adjacent L over r, which when we solve for theta gives us a theta of approximately 54.37 degrees. I'm going to keep some extra sig figs there for our calculations. So what's the tension of the rope and what's the force on the sphere by the wall? Okay, so this one here we can actually do with just forces, so without torques, I believe. So let me see. Let's draw a free body diagram for this case. So free body diagram, there's going to be here force downwards on the ball. There's going to be a tension that way, and then there's going to be a force from the wall, right? There's going to be a normal force from the wall pushing on the ball. So I can break this one here. I'm going to break the tension into x and y components, right? So this, if this is theta, then this is going to be t cosine theta for the x component and t sine theta for the y component. So here we just do a simple sum of the forces in the x direction equals 0, and sum of the forces in the y direction equals 0. So sum of the forces in the y direction, the force upwards is going to be due to tension, right? So it's going to be t sine theta, and then the force downwards is going to be the weight. And for the x component, the force to the left, to the right, the positive force is going to be the normal force to the wall. Then there's going to be a force from the tension. T cosine theta equals 0. The only equation with one unknown is the y component one, so let's solve this for t. So t is going to be equal to the weight over sine theta. And the weight is mg over sine theta, so m is 1 kilogram, theta is 54.37 degrees. So we solve this and we get a tension of about 12.06 newtons. So we can plug that over into here now. So solve that for normal force is t cosine theta. So the normal force, when we plug it in, ends up being about 7.02 newtons. So there is our normal force, and there is our force of tension for this ball hanging. So in this case, we could do it without doing any torques. This next one has, from the textbook here, has 2 blocks hanging. They're tied by 3 strings. And it says here, it's an equilibrium with the string. The center is exactly horizontal. A has a weight, so the weight for A is exactly 40 newtons. The weight for B is 50 newtons. And we have one of the angles, it's 35 degrees. And it asks us to find the 3 tensions and the angle theta. So we can write down all kinds of equations to calculate this. This one here, again, I think we can do without any torques. So let's do block A, or the point right above block A here where the 3 strings meet. So right above block A, there's going to be a tension attached to A, and that's going to be equal to the weight of A, right? Because the tension is canceling out the weight of A. So there's a tension that's equal to the weight of A. There's going to be a tension 2 here, and then there's going to be this tension 1 here with this known angle phi. And then for the other, above the other block, there's going to be a tension B downwards, which is going to be equal to the weight of B. There's going to be tension 2, it's the same string attached to A. And then there's going to be tension 3, right? And so our unknowns in this case are tension 1, tension 2, tension 3, and that angle theta. So we have everything we need here we could possibly hope for to figure it all out. So let's start, let's start by doing the sum of the forces in the y direction on above block A. So if I go the sum of the forces in the y direction, so this is at the point above point A, right? It's equal to 0. So let's see, what are the forces upwards? Well, there's a component of the tension, right? Tension 1, it'll be cos or sine. It'll be cosine phi upwards minus tension A, which is equal to the weight of A, and that's equal to 0. So that gives us tension 1 right away, right? Tension 1 is equal to the weight of A over cosine phi. When we do that, we get 49 newtons. So 1 down. We can also do the sum of the forces in the x direction to get more information. So let's go, so that's one of them. So let's put a box around this. So for the other one, I'm going to do the sum of the forces in the y direction is equal to 0. Not the y direction, the x direction. So the force to the right, the positive force in the x direction is that tension 2. And then there's going to be a component of T1, which will now be sine of phi is equal to 0. So now we can solve this for T2. T2 is just T1 sine of phi. So when I plug in my values there, I get 28 newtons. So now that's our second one. So now we have T1 and T2. This one's working out pretty easy. Let's look at for for the other one. So the other one, the forces at that point above B, we have the three. We can do the sum of the forces in the y direction equals 0. So it's going to be T3 cosine theta is equal to, or no, minus the weight, or minus the tension B, which is weight B, is equal to 0. So that's one of them. But there's also the sum of the forces in the x direction is equal to 0, which is T3 sine theta 3, and that's going to be minus, because that one's negative, plus T2 is equal to 0. We have two unknowns here, right? We have T3 and theta. So what I'm going to do is I'm going to eliminate one of these. So what I'm going to rewrite this one as T3 cosine theta equals weight B. This one, T3 sine theta equals T2. So if I just do equation 1 divided by equation 2, that's taking everything on the left side of equation 1 and dividing it by everything on the left side of equation 2. T3 sine theta, that's the left side of equation 1, divided by the left side of equation 2, T3 cosine theta. And the right side of equation 1 is T2, and the right side of equation 2 is B. And you notice that these cancel out, and sine theta over cosine theta becomes tan theta. It's equal to T2 over that. So theta is the arctangent of T2 over WB, and we get 29.25 degrees. And then I'm going to plug that back into equation 1, which I'm going to rewrite as T3 is equal to T2 over sine theta, and I get, where's my answer? I get about 57.3 newtons. Okay, so there's one and there's the other. So we have calculated all the unknowns using the sum of the forces equals 0. Now, in this case, we have a long beam that's attached to a wall, and it's also suspended by a cable. Okay, so and let's write down everything we know here. So we have that the length of the beam is 4 meters. We have that the height of the point that the cable is attached is 3 meters. And we have the weight of the beam is given as 500 newtons. That's the force of gravity on the beam. And it's asking to find all the forces on the beam. Just preemptively, we can calculate theta, right? Tan theta is equal to d over L, opposite over adjacent. And that gives us a theta of, in this case, 36.87 degrees. So what are all the forces in the beam? Well, let's draw. In this case, we're going to need torque. So let's do an extended body diagram here. So there is the beam. There is going to be weight in the middle of the beam. We're assuming that, usually we assume that the force of gravity happens in the center. There's going to be a tension, due to that cable. We know this angle here. And that beam is attached to, you see here the beam is attached to the wall via like a vise or something, or a grip or something like that. So we're going to assume that there's some two-dimensional force here, and I'm going to break it into two. I'm going to call this the horizontal and the vertical force. So there's some force here. Instead of doing an angle and a magnitude, I'm just going to call the two components V and H for horizontal and vertical. And what are all our unknowns? We have 3 unknowns here, right? Our unknowns, so unknowns are the vertical component from the wall, from the hinge, the horizontal component from the hinge, and the tension. So we're going to need 3 equations for that. So we're going to do the sum of the forces in the x direction equals 0. We're going to do the sum of the forces in the y direction equals 0. And we're also going to do the sum of the torques is equal to 0. And for the torques, where you pick your pivot point can help you a lot. If I pick a pivot point here, I'll have 3 unknowns in the equation, right? One due to the tension, one due to V, so I'll have 2. If I pick it here, I eliminate V and H. So I'm going to pick here because those positions will be exactly where the pivot point is, so there will be no torque. So that's going to be my pivot point for my torque. So let's write down the equation. So what are the horizontal forces? Well, the horizontal forces, the positive one is going to be H, and then there's going to be a horizontal component of the tension, right? So it's going to be T cosine theta is equal to 0. For the y component, there's two forces. Oh, I'm missing. No, I haven't. Yeah. So what are the forces in the y direction? Well, in the y direction, there's more. There's two upwards. There's going to be the vertical. There's also going to be a component of the tension that's upwards, right? So T sine theta, and then there's the weight downwards. And so now for the torques. For the torques, we need the distance. So we need the distance of this thing here. How far is the weight from the pivot point? Well, it is halfway out, so it'll be 2 meters. Excuse me. And how about this tension due to the torque due to the tension? That one is all the way out at the end, so it's going to be 4 meters out. So now we can calculate, we can write down the equation for the torque. So there's going to be the torque due to the weight, and that's going to be clockwise, so it's negative, plus the torque due to the tension. That's counterclockwise, so it's positive. So we have our 3 equations and our 3 unknowns now. So let's look at how to solve these. Well, let's plug in for the torques first. So the torques become, let's see, the torque due to the weight will be, the weight times the distance, which is d2, or d weight. And the torque due to the tension, well, that's going to be the tension times the distance due to the tension. This one's not at 90 degrees, so we need to include the sine of that angle, theta, is equal to 0. So now we can solve this for the tension. The tension is going to be equal to weight times that distance divided by that distance, sine theta. When I plug in all my numbers here, I get about 417 newtons. So that's the tension. We have one of them down, 2 to go. Now that I have the tension, I can plug it into here to get V. So if I solve this for V, it's weight minus T sine theta. So if I plug in for the tension, I get that the vertical component of the force is 250 newtons. So that's good. And we can also plug it in to here to get the horizontal force. So that will be T cosine theta. And when I plug into there, I get 333 newtons. Ta-da! So now let's have a look at the next one. So here, another one I found from the textbook that I like. Someone's trying to get his car out of the mud, so he ties a rope here tightly around a pole 18 meters away. So this distance here is 18 meters. He then pushes sideways right here upwards, and he displaces the rope by 30 centimeters, and he pushes with a force of 550 newtons. So what's the magnitude of the force of the car on the rope? In other words, he's pulling up here, and that's going to cause a tension, right, that the rope is pulling on the car. So if we look at that one point, so he's got some force upwards here, and there's going to be a tension this way, and we'll assume the same tension that way, like this. And it's asking us to find the tension of that car, or the tension of that rope. So we can find the angle that we need first. Let's see. This here, he pushed it up 30 centimeters, so this is 0.30 meters, and half of 18 meters is 9 meters. So tan theta will be 0.3 over 9. So that gives us a theta of approximately 1.90 degrees if we solve that for theta. So we have this angle here, theta, and we're trying to find the tension. So we can just say that the sum of the forces in the y direction equals 0. So what are the forces in the y direction? Well, there's the force upwards, and remember that force he's applying is 550 newtons. And then there's the y component of the tension downwards due to 1, and the y component of the tension due to the other one downwards, right? So that's F is equal to basically 2 times Ty. So Ty is just going to be T times, let's see, if that's theta, then it will be sine theta. So solve this for T. So T is going to be equal to the force over 2 sine theta. So we plug in 550 for the force, plug in 1.9 degrees for the angle, and that gives us 8,300 newtons is the tension that he's able to exert on the car by pushing on that rope upwards. So let's have a look at this problem here. So here is some crazy L-shaped structure, and there's 3 forces, F1, F2, and F3 acting on it. So there's F1, there's F2, and there's F3 acting at different points, and we have A's and B's given. Now it's asking, we have these 3 forces acting on it. It wants to know what force do I have to exert at some point P here. It'll have a horizontal component and a vertical component, some distance D. It's saying what force do I have to exert such that all this stays at rest. Okay, so we want to find F vertical, F horizontal, and D. And so the way you do that is we set up our sum of the forces in the x direction equals 0. You know, we're going to set up our sum of the forces in the y direction equals 0. And we're going to do our sum of the torques equals 0. Now, for our torques, we're going to pick, you'll see, we're going to pick the torque around the origin here. And if we do all those torques, they add up to 0. So let's sort of plug in everything we know. So some of the forces in the x direction. Well, there's one force to the right. It's FH, right? That's the force we're applying. There's one force to the left. That's F3 equals 0. That immediately gives us FH, by the way. Solve that for FH. FH is just equal to F3. So in other words, FH, if you look here, F3 is given, it's 5 newtons. So FH is 5 newtons. So we're 1/3 of the way done already. Some of the forces in the y direction. So we have the vertical force that we're applying, and then there's minus F1 minus F2 is equal to 0. So solve that for FV, and that's equal to F1 plus F2. So that gives us FV of 10 plus 20, 30 newtons. We have 2 down, 1 to go. So here we are going to, from here, what are all the torques? Well, there's a torque due to 2 minus torque due to 2. That you see that this torque due to force 2 is trying to turn it clockwise, so that's negative. There's also going to be a force due to the vertical applied force. That's going to be plus torque due to the vertical, and that's going to be counterclockwise. And there's also going to be a force due to 3, which is also, you see this one here, is also trying to turn it clockwise. So T3 is equal to 0. The nice thing about torque 3 is to make it easier, we can just consider it here. Say F3, and then this here will be D3 perpendicular, which is just equal to A, right? We just consider the perpendicular component. Instead of trying to find this distance here, it's easier to just consider the perpendicular component of the distance. So let's plug in for our torques. So T2 is minus the distance to 2 from point O, which is listed as B, times F2, and they're perpendicular, so that's sine of 90, plus the torque due to, let's see, the torque due to the vertical is going to be dF vertical, and then minus the torque due to 3, which is going to be minus A F3 is equal to 0. So I solve that for D, and I get BF2 plus AF3 all over FV. When I solve that, I get about 1.3 meters. Okay, so that's using 3 equations to find 3 unknowns. For our last one, I came up with this fun little problem here, right? We have a 40 kilogram black steel bar, and to it is attached a sign for a taco shop. Find all the forces on the bar. So I'm just going to set this one up and leave this one for you guys to work out, and here's the bar. I'm going to do an extended body diagram. So we want to find the forces on the bar. So what I like to do is it's attached to the wall. So I'm going to assume that there's a horizontal and a vertical force, kind of like what we did with the other one. And there's going to be the weight force from the middle, right? So this weight force here is going to be mg. And what's the distance here for torque purposes? This distance here, it's in the middle, so it's a 3-meter bar. So this will be, so this here will be 1.5 meters. What are the other forces? Well, you notice that the sign is attached at 2 points. Okay, so there's going to be 2 tensions downwards. One due to this one, and we're going to assume here in this case that they're the same. That T1, that they're both T1. That TS exerts the same force downwards on both of them. And we know what T1 is going to be. It's going to be half the weight of the sign. Okay. And what's the last force acting on this? Well, there's going to be the force of tension, right? It's going to be tension 2 here. You need to figure out here, this angle here. Oh, it's given as 30 degrees. So you can find, so our unknowns are V, they are H, they are T2. And T1, you can just assume T1, it's evenly splits the weight of the Cotijas sign. So even though T1's an unknown, that's easy to figure out.